we are going to see conservation of linear momentum. Now, from the examination point of view, conservation of linear momentum is actually a descriptive question. Okay, you might be getting a 5 marks question on that. So whatever we are going to do from now onwards, I don't think we can finish it today, but we'll finish it by tomorrow. We will have it as a descriptive question. So please concentrate on whatever we are going to derive. Okay, and then if you have attended the last 2 or 3 classes, some of this technical term will already be known to you. So what can be the question? Okay, the question would be, discuss the conservation of linear momentum if the coordinate corresponding to the displacement is cyclic. Okay, so let's just go one by one. Whenever we say conservation, what does it mean? It means that if there is a process which happens, let's say a reaction, a collision or whatever, okay, the momentum does not change before or after. It remains conserved, it remains same. So if you basically consider any closed system, you know that the total energy will remain conserved. So that is what is conservation is all about, more or less. Okay. So here also we are going to look into that conservation of linear momentum. And as we have seen in the last class, mathematically when we talk about conservation, we do say that del P or let's say del T will be 0. Just an example. Okay. So if this is 0, that means this P has to be constant. So that is conserved. So that is what is conservation is all about here, and this is something which you are going to look into it numerically, mathematically. Okay, we're going to go step by step. I'm going to do a detailed derivation, so don't worry. And if the coordinate corresponding to the displacement is cyclic, so you already know about displacement. Displacement is basically a vector quantity, so it does have a direction and magnitude, and it is cyclic. So it means that it is ignorable. That means if we consider the Lagrangian, we have not yet discussed Lagrangian in detail, but we know that Lagrangian is a function of the generalized momentum, generalized velocity and time. So if we consider any of the values, let's say qk, in this particular thing, let's say qk, which is a general coordinate, okay, and this is independent of, this does not appear in the Lagrangian. So you can say del qk divided by del L is equal to 0, right? So that means this qk is nothing but called the cyclic coordinate or the ignorable coordinate. So this will be the question. Okay, if I don't give the condition that the coordinate corresponding to the displacement is cyclic, then you cannot really prove this. Okay, so it becomes a bit difficult. So we are just going to, so as I said in the last class also, pardon my handwriting, not very good, but then I will read it through and you can make your own notes. So what happens is, if you basically, so see, whenever you write down an answer, it's very important that you give a very good opening statement. Okay, just as in a debate or in a presentation or in a lecture, an opening lines are very important. Okay, even in a movie. So everything works the same in life. Please make sure that you start with a good opening line. Don't straight away start with writing down the equation and explaining. Okay, I think that is not a good idea, because the last class also I told you that whenever you write down an answer, you keep it in your mind that the person who is reading this doesn't know anything. Okay, you have to make that person understand. So that is important. So if you have a coordinate corresponding to a displacement is cyclic. So as I said, that coordinate in this example might be qk, does not appear, okay, does not appear in the Lagrangian. Okay, so we say that then the translation of the system has no effect on the problem. So if that particular coordinate is cyclic, does not appear in the Lagrangian, even if we translate the system, it will not have any effect on the problem. Okay, it won't have any effect on the problem. For example, let's say I consider a frictionless surface and I move a body. So in general, practically, maybe there won't be any frictionless surface, no perfect frictionless surface. But then if we consider it theoretically, we know that there is no energy lost. So that a frictionless surface, the coordinate associated with it will be more or less cyclic in nature. Okay. So in general, we can say that the description of the system motion remains invariant. So invariant is another term which might be a bit technical, but I think this is very simple. It does not change, it does not vary. Okay, and the linear momentum is conserved. So this is your opening line. The linear momentum is conserved under such translation when the coordinate is cyclic in nature. Okay, so please make sure you understand this, and then we can actually go to a bit of generalized coordinate idea. So what we do is we represent this Qj, which is called the generalized coordinate. So I think Qj, we have been using it time and again as generalized coordinate, so should not be a problem. So Qj is your generalized coordinate, and dQj will actually represent the translation of the system as a whole in some direction. So you know, whenever you put a d before, let's say, any variable x, y, t, okay, we say in general say that there is a small change. Okay, so this dQj will actually represent the translation of the system as a whole in some direction. So you have Qj as one of the generalized coordinate, and dQj will actually represent the entire system's translation. So this Qj will not appear in the kinetic energy. I think this is something which we already have seen. Okay, this Qj does not appear in the kinetic energy relation. So kinetic energy is half mv square, dependent on velocity. Does not depend on the position, just like we do with potential energy mgh. So it does not appear there. So we can say that it depends only on the velocity, which involve the derivative of displacement and hence unaffected by the shift in origin. Okay, so try to understand this in a very simple way. Don't try to complicate here. Okay, don't try to think it in a very complicated way. That is there. Okay, it's half mv square. Okay, so half mv square means it's basically a function of the derivative of the displacement, because v is equal to dx by dt, right? So dx by dt. So it is a derivative of the displacement. So that means when we talk about it as half mv square, we are saying it doesn't depend on the displacement directly. So we can say that del t del qj dot is equal to 0. You can do it also. ddt of let's say ddx of half mv square will obviously be 0, because it does not depend on x. So we'll do that. We'll take this consideration into the picture. So please note here that these things you already know. But then when you are used, sometimes feel that oh, this is very trivial, but there is a way to write it in classical mechanics. Okay, so the way you write is very important. Okay, it's simple, but you have to write it down in terms of classical mechanics. That's important. So what we do here is we actually consider a conservative system. So you know, in the last class I said what is conservative system. Okay, in terms of the potential energy that it has. Okay, the potential energy del V del Qj dot will be 0, and then del V del Qj will exist. Okay, this is something which you already know. So when we talk about this, I think this line also I have told you, so I don't think it's very difficult. V is equal to mgh, right? So we can say that del V del Qj dot, or Qj dot is nothing but a velocity, right, is 0. Why? Because V is mgh, and mgh means it's a function of only position, not velocity. So that means this will become more or less 0, right? So that is why it is 0. And then of course del V del Qj exists, of course, because position is there. So there is some coordinate which is present. So that's there. So we can write down the Lagrange's equation of motion, and don't get confused here. Okay, this is important because Lagrange's equation of motion we have not yet derived, but we are using it here anyhow. Okay, so right now we know that Lagrange's equation of motion is ddt of del L del Qj dot minus del L del Qj is equal to 0. Okay, and then what is del L del Qj dot? So you know Qj dot is there, and then L is equal to T by T, T minus V, sorry, and del L del Qj dot will be del T del Qj dot. Okay, because L can be written as T minus V, and then you can replace it L as T minus V here, this one. And if you just do the differentiation, you separate it out. Del V del Qj dot is 0, as we said, so it will just be del T del Qj dot. Okay, so we can just replace this del L del Qj dot by del T del Qj dot. Please note, okay, this is important, you have to understand this, don't memorize things, very important. Minus del L del Qj now. Del L del Qj. In the last slide, we said that del T del Qj is equal to 0. This part, del T del Qj is equal to 0. Let's consider this now. Del L del Qj. So del L del Qj, we can write it down. Okay, this my pen tablet is giving some problem. I really cannot write it properly. Whenever I'm writing it, there is some lines which are coming out. See, it comes this way, very difficult. Okay, so we have got this del L, so this is T minus V. So del T del Qj is 0, right? This part is 0. That means this will only remain with del V del Q minus sign. It is minus, so it is minus of del V by del Qj. This is V, okay? This is not L. Sorry for the handwriting. I've just overwritten this too much. So minus del V del Qj is 0. So we can write it down as d dt of Pj. Now you again tell me where do I get that Pj. So if you remember that what I said in the last class, that P del T del Qj dot is nothing but Pj. We have derived it, okay, in the last class, which was actually nothing but the generalized momentum. I also showed you why del T del Qj dot is actually momentum. When we put T is equal to half mv square and then we put the appropriate coordinates, we see that when we differentiate it, we are actually going to get mass into velocity. So that means del T del Qj dot is nothing but the momentum. So this is basically called the generalized momentum. So we have got ddt of Pj is equal to, we'll take it on the other side, it is minus del V by del Qj. Okay. So when we do it, we get that Pj dot. So ddt of Pj can be written as Pj dot, and Pj dot is minus del V by del Qj. This can be written as capital Qj. Why? See, this is nothing but rate of change of momentum. Rate of change of momentum from Newton's second law is nothing but force. Okay, and that's why this is nothing but the rate of change of momentum. And rate of change of momentum must be equal to force, because whether you consider classical mechanics or any other field or any other way of deriving a relation, the fundamental doesn't change. The Newton's second law will remain as Newton's second law, right? Rate of change of momentum will remain as force. So that's why this is nothing but force, remain as force. And then we found out a new relation here, that this force is nothing but minus of del V by del Qj, where V is the potential energy and Qj is the generalized coordinate. So you see this and this is okay, can easily remember, you know, but this one is something which you are deriving here. This is something which you found out additionally. If you look into the dimensions and all, you will see, yes, this is force. Okay, this is force, so it's not a problem. You can always go for the dimensions and derive it. Okay, so dimensionally, how do you understand this? I think this is simple. This is potential energy, sorry. So this is mass into acceleration due to gravity into height. So height has a dimension of, let's say, meter, okay, length, and then delta Qj again has a dimension of length, because this is a coordinate, no doubt, but it is a measurement of length. If we don't consider it in terms of angle, so it's length. So it is again length. Above we have height is length. So length like that cancel. We just have got m into g, mass into acceleration due to gravity, which is nothing but again force. So in exam, what I will suggest is, not only for my paper, not only for this course, whatever you do, okay, be it entrance, be it any other paper and any other course, you are reading a book, always go and check for the dimensions. Okay, sometimes you might jumble up, I'll also jumble up, I'll also get confused, but the thing is, when you know the fundamental, you put all the dimensions there, plug in everything, you should see that the dimension remain the same. So if I say this is force, okay, if I say this is force, this should also be force. So this comes out to be force. That means this is correct. Okay. If this is wrong, you can ask me why this is not force. Okay. So please make sure you do that. I think that is a good practice. Not yet over. I've just given the heading as generalized force because we are explaining generalized force here. But then this is a continuation of this. Okay. The conservation of linear momentum. So whenever we say Qj, this is nothing but the component of the total force. So we know that this is nothing but the force. This force is along the direction of Qj and Pj. So that means if we have a force which we cannot relate to Qj and Pj, we cannot call it as a generalized force, right? because we know that whatever we are differentiating or whatever derivation we are doing it in terms of Qj and Pj. So if you are doing it in terms of Qj and Pj, we actually want to relate this Qj and Pj with force. So that means this force capital Qj should be related to small qj and pj. So this is just a notation. Don't get confused. You might tell me that why I am writing down capital Qj as generalized force. Can't I? The thing is, there are certain conventions which are being followed. So capital Qj in general in classical mechanics is represented as generalized force. Please make that clear, okay? And don't get confused during exam. Whenever you write down, don't overwrite things so that I get confused in checking your scripts. Just write down Qj, and if you have written by mistake small qj for generalized coordinate, just cancel it out and write down capital Qj. So if capital Qj, so it can be shown along the same direction as small qj and pj, then equation 1 represents the motion of total linear momentum. So you know, when we talk about this relation, this is the rate of change of momentum. So in general, when we talk about force or Newton's second law, we are talking about the rate of change of linear momentum. So we are not talking about the rate of change of angular momentum. Why? Because when we talk about rate of change of angular momentum, this is not force, this is torque. So we are not talking about rotational motion here. Okay. So each and every word, whatever has been written, okay, is important and it carries some meaning. So that is why when we say that this capital Qj can be shown as the same direction as small qj and small pj, then it will actually represent the total linear momentum. It has to be along the same direction. So if it is not along the same direction, there are some chances that the system will rotate. And if it rotates, this won't be linear, this will be a circular motion. And then we call it torque and not the force. Okay? So that's why it's important along the same direction. So that's there. Okay? So when we talk about generalized force here, okay, when we talk about generalized force, we want to actually represent the direction also. That's very important because we say along the same direction. So this generalized force can be written as summation of all the forces. Here I have written capital Fi because we are considering individual forces here, not the generalized forces. E2 or dot product with the direction. So I think this is also clear to you. You know how to represent directions. Okay, you already know how to represent directions here, because whenever you consider a case where you have position vector, okay, and we differentiate it with respect to one of the coordinates, we are actually defining the direction. Okay, so Ri is the position vector and dqj is the component in the direction. So if you basically consider the x coordinate, okay, if you consider this and then this is your r, okay, this is your r and then this is your x. If you write down del r del x, you are actually defining the direction there. Okay, very important. So here also we're doing the same, del r bar divided by delta x, and then we say that n cap is the unit vector along the direction of translation. Okay, so we can say that this is represented by n cap. So I can just simply write it down. Delta ri is nothing but n cap delta qj in the direction of translation. Okay, so just a way of representing it in terms of vectors. Okay, it's nothing physics here, it's more of maths and vectors. So n cap into delta qj, so you can just replace this delta ri by n cap into delta qj. Okay, so in simple words it means that what is the direction of ri? So we are considering the delta qj component in the direction of qj, and since we are representing the direction, we are representing it in terms of n cap. Okay, so we're not really saying whether it's in the I direction or the X direction or the Y direction. Okay, because you will see that when we consider certain things in general classical mechanics, we are keeping it generalized. So we're taking it as n cap. So n cap delta qj, replace it here, and then this delta qj gets cancelled, we get n cap. Okay, this is n cap, sorry, not r cap. This is n cap. So this is n cap. So you can just replace it here. So that means that generalized force can be represented as Fi into n cap, which is n cap into F. So in exam you tend to write down directly. Why should I try to understand so many things about delta Ri by delta Qj dot? एग्जाम में मार्क्स ही तो चाहिए. I can directly write it down as capital QJ is equal to n cap into f. But I think from understanding point of view, where does this n cap comes from? I think that is important. That's why that derivation is important. Okay. So you can see we are doing a lot of things. So obviously this is a long derivation, and I think we need to understand it step by step. So this will be a descriptive questions, not less than 5 marks. Okay. So this actually represents the component of the total force. So this actually Qj, which is the generalized force, is written as n cap dot f, represents the component of the total force along the Qj direction. Along the Qj direction. And you know Qj and Pj are related. Okay, Qj is the generalized moment coordinate, Pj is the generalized momentum. So they are related. So if I can represent it in the direction of Qj, I am also talking about the direction of Pj. So, okay. So this is the representation of the generalized force in the direction of Qj. So this kinetic energy that we are actually talking about is half mi dot square. Just go back to the basics again, and then find out the generalized momentum now. Okay, we're going to use all these for the final derivation. Okay, so what happens is Pj is equal to delta T delta Qj dot. So what happens is equal to summation I mi dot. We can just replace it, and del ri del Qj dot. I have shown it here. You can just take it del Qj dot, because del Qj dot is here of T. And T half of m is okay. That is a constant. You can take it out. Okay. Only you have to differentiate it with respect to Ri dot. So del Ri dot of Ri dot del Ri dot by del Qj. So this del Ri dot will get cancelled. I'll get back the same thing. So when you differentiate this part, okay, when you differentiate this part, you get 2 Ri dot and del Ri del Qj dot. So 2 Ri dot del Ri del Qj dot. We have it here, and that 2 and this 2 will get cancelled. Okay. And then as a result, I'll get this relation. So this is the generalized momentum. Okay, we already have seen it in terms of kinetic energy, but we can also write it in this way. So there are different ways of writing it, but anyway, we are going to use it. Okay.